Hello, everyone. Welcome to this course on BGP. We saw that one of the subtle technicalities of BGP is how the information that is learned by BGP, like in R6 and R2, is passed into the entire network. For example, how does R1 know what to do with packets that are outside, that have a destination address that's outside the domain? We have seen that one solution is to redistribute BGP into the IGP, into SPF, for example, but that loads the IGP with all the prefixes that are exterior. So an alternative is to use BGP everywhere, which after all leads to about the same work to be done by the routers. Yet another alternative is to avoid the problem entirely, at least if we don't require that R1 is connected to hosts that want to speak with the outside, which is very often the case, is to use source routing. But that one is a bit theoretical. The alternative that is used, we will not try it in the lab because we will not run Mpls in the lab, is based on Mpls. So what is Mpls? We'll talk a bit about it in the last week. Mpls is something that is very little known, but much of the internet runs in the backbone with Mpls. It stands for multi-protocol label switching. Mpls uses labels. We've seen labels already with virtual LANs. When we have a virtual LAN switch that has multiple virtual LANs, in fact, it may send the packets to another virtual LAN switch by adding to the packet a virtual LAN header. So an Mpls header is not a virtual LAN header, but it's very similar. It's a number that is added at the Ethernet level, and that allows, for example, when R2 wants to send data to R6, then with this solution, what it will do, they will establish what is called an Mpls label switched path that has the effect that R1 is now not just an IP router, but is a combined IP and Mpls router. We look at the labels, and for example, at R2, when R2 learns by BGP that this prefix has next hop 222, then R2 will build a label switch path to R6, because R6 is the router that connects to 222, and allocate a label, for example, 23. When R1 receives such a packet, so this label is put in the Ethernet header, it's below IP. When R1 receives this a packet with this label, if the setup is correctly done, then the R1, by just looking at 23, will forward the packet to R6. Then R6, which is at the edge of the network, will remove the label, and then we'll do the usual business. But for R6, it's easy because R6 has a next hop, which is on link here. So this is a bit mysterious. Why we do that? We'll talk about it a bit more in 2 weeks, probably. Functionally, it is exactly like encapsulation or source routing. It's like saying, after all, I have packets that must transit my network, and all the transit part of my network doesn't need to know exactly all the details of the internet. All they need to know is how do I reach the edge, R6 or R2. We've seen we can use source routing by putting the source routing header R6. The labels here are a form of creating a tunnel, in fact. We'll come back to Mpls. Right now, in the lab, in contrast, we will be confronted with some weird side effects of the fact that routers treat BGP at the same level as OSPF. There is no hierarchy. We've seen that a symptom of that is when we see that BGP injects into the forwarding table the next hop, for example. When we do that, there can be injection conflicts. An injection conflict is when several parts of the routing protocols can lead to information about how to go to a next hop. Essentially, we will see an example. We've seen that BGP may inject a route, but also OSPF may know about the same information if we redistribute BGP in OSPF. In such cases, you will have multiple lines in the forwarding table with the same destination. But it is not like we've seen that in the case of OSPF. It was intentional in the sense that we wanted to do equal costs multipath. We may have multiple paths, in which case we're happy to have multiple entries in the routing table, and we will split them as we have seen, by using a hash of the flows to distribute evenly or according to some other proportion on the different path. Here it's a different story. We have different routes that are coming from different logic of the system. And what is done in that case is to add another field, which is a priority field on the route, which is called the administrative distance. So in the forwarding table, if we look at it in the detail with FRR, as in the lab, you will see that there is a forwarding and table entry contains the destination, the distance to destination, and in addition, there is an administrative distance, which is simply a symptom of which routing process wrote this table, this information into the routing table. We are concerned here with 3 instances. It can be written by BGP. It can be written by BGP Ebgp. Ebgp means the router has learned about this route from Ebgp. In other words, it's first-hand information. Or by Ibgp through the BGP mesh, or by OSPF, perhaps, because it's redistributed. And this is a priority system, so lower means better. Let's see an example. Here, we're focusing on the same tome example. So we assume that here we do redistribution. So forget about source routing or Mpls. Here we do redistribution of Ebgp into OSPF, which is, I would say, what you read in many textbooks. That's the normal, from a pure logical way, that is what we could imagine to do. So all the external routes that have been learned by R6, for example, from BGP will be put into OSPF, and therefore R1 will learn about this route, and R2 also will learn about the route 18.1. Let's see an example that shows the conflict that may arise. Assume at T1, R2, which is here, injects into its forwarding table the information it has learned about this prefix 18.1. So it will write destination, next hop 222, and then an administrative distance that says essentially by which means did R2 learn about this route. Here the means it is Ibgp. Ibgp has the least priority because this is second-hand information. Now let's continue. Assume at a bit later, or all those things are happening in parallel. It may not necessarily occur in the order that I said. Let's assume R6 here injects at a later time the route 18.1 into its forwarding table, right? And it will therefore be redistributed from BGP into OSPF here. So at R6, we will see this route here that is learned by Ebgp, so administrative distance 20. Then this will propagate by OSPF because OSPF takes all the things that have been redistributed into OSPF. So by OSPF, R2 will learn about this. That's the goal of the redistribution of Ebgp into OSPF. So now R2 will learn about this prefix with a distance that is given here will be the distance from R2 to R6 plus the distance that has been put here when Ebgp writes into the forwarding table this external route. Now, what is the value that should be done? In fact, we don't know. But this version of Cisco's software used a default cost of 20. So here R6 says, I know how to go to 18.1. It is on this interface. And the distance for me is 20. That's a standard default for Ebgp injection into the routing table. Therefore, R2 by OSPF will compute a distance of 22. That's a OSPF distance here. Now, it was also, this route also existed. It had no OSPF distance because it was injected from Ibgp. So we have now 2 routes that are injected here. The first one comes from OSPF. OSPF has computed the next hop by the classical Dijkstra computation of how to go to 222. The next hop is R1 East. And this is another one here. Which one should we use? Well, obviously the first one, because this is easier. We will not need to do a lookup, a recursive table lookup. And it is safer to use it because we redistributed BGP into OSPF. This is exactly what happens. OSPF has a smaller administrative distance than Ibgp. So, in fact, this route will not be used at all. except if for some reason OSPF doesn't work. You may wonder why we do that, and I do wonder why we do that. If I would redesign a router from scratch, I would probably not do things in this way, but this is how this is done. My interpretation is that there were multiple ways of injecting the routes into the forwarding table. Then people quickly recognize, well, if there are multiple ways, we have a potential conflict, and we'll resolve it in this way. Voila, so those are the nitty-gritty details of how BGP really works. You see also some distance somehow from the clean architecture and how we imagine things are from when we do it in details. Some things, some practical things need to be solved, and they're not all solved according to the most beautiful design, but it works. What we will see now is other bells and whistles of BGP, in particular priority fields. One of them is local pref. Local pref is essentially a field that an autonomous system assigns to say which priority it gives to a given route. As I mentioned several times, at the level of autonomous system interconnection, there is a very, very meshed interconnection. So many, we've seen, for example, that all the providers that are at the top of the hierarchy, the tier 3 providers, they must connect to all other providers. So they have a lot of possible interconnection, and they may decide to give priority to some, for example, based on business agreements that they have or whatever decisions that are also sometimes political. It may be that if an ISP is under the control of a government, it may be political decisions. So for example, here, when a given route coming to a given destination comes from this side, we may decide to give it a preference of 100 versus a preference of 10 if it comes the other way around. And this preference is typically given by the configuration of your router for things that you get over eBGP, and it's propagated without change over IBGP. So all routers inside the domain will inherit the preference that is given when the route is learned from the outside. Here is a concrete example that illustrates why we would do this. Assume here AS4 is connected to AS2 and AS3 over a link here that is shown in this shaky line, which means it's a link perhaps of poor quality, or is very long, or costs a lot. So it exists, and because we are meshed with a number of people, we keep it. It may also serve as a backup, but we would prefer not to use it. So in this case, AS4 may decide to set local pref to 100 to all routes received from AS3 and 50 to all routes received from AS2. So R1 receives, for example, an announcement for the prefix 10.1 over eBGP, will set the pref to 50, whereas R2 will set the pref to 100. If that happens, what are the possible cases when R3 announces this route 10.1 to AS5? What are the possibilities for an announcement here? I close the poll in a few seconds. The majority says B. It is sometimes difficult to do a quiz that has a non-ambiguous answer, so it is probably the correct answer, yes. B is possible, and because here R3 will receive via IBGP those two routes with a different preference, a higher preference from the one coming from R2 and a lower preference. So the decision process will have to compare the two. They have the same AS path length, everything is the same except the preference, so it will give priority to the route that was coming from AS3. So this is a valid answer. Another valid answer is none. It is also possible that AS4, due to policy, refuses to export these routes. This is also a possibility. C is certainly not possible, right? Because we know that R3 can export only a route that it has chosen as best route. You cannot export the two. You cannot propagate the multiplicity of information. So R3, if it picks a route, will pick this one. Therefore, if it announces a route, it will announce only this one. So this is how policy can be implemented also in the internet. There are probably more than 100 attributes to a route, so there are many others like weight. Weight is also a priority field that is local to this router. So it's a manual way. If you want to force the decision process to prefer one route due to some whatever reason you have locally, one way, because you typically don't change the logic of the decision process. The BGP will apply all the rules in sequence and stop whenever it finds something that is better. So if you have an out-of-band information that you want to prefer this route, then you can do it by giving a high weight to this route. The weights do not propagate to other routers, so this is just local information, unlike the local pref. Here is another field that's very similar. It's called the MED, Multi-Exit Discriminator, which is used in this typical scenario where you have a provider here, X, and a customer, Y. And very often a customer, if you use BGP, you're probably a large customer, not you and me at home. So if you're a large customer, you probably also are connected at multiple points to your provider, like Swisscom here. And you would like to signal to the provider what you would like to happen. We've seen last week in the toy examples that there are multiple ways the bottom network, the YAS, could advertise, for example, here 10.1 and 10.2. We've seen in one example, which is this one here, that both routers R3 and R4 advertise the entire set of prefixes that exists in the network. We've seen another example where every router would advertise only the prefixes that it can reach locally. So both are possible, but certainly the former is preferred because if you if you have some connectivity here, it's better to announce everything. In case, for example, this link dies, you will still be able to reach this path through another path. If you announce everything, you may still want to have some control on the routing that is done by your provider. Is it hot potato or cold potato? If there is traffic that's going to 10.1, do you prefer that it goes this way, or do you prefer that it goes to the closest exit? We've seen that it will tend to go to the closest exit if you do nothing. That's the hot potato principle, because eBGP has preference over IBGP. So if a router in ASX knows a route to 10.1, for example, exported here, a packet to 10.1 would be sent, if it comes at R2, would be sent here and not traverse the provider to get here. Very often, if you have a provider that you trust and whom you give the job of managing connectivity for you, you want the traffic to be handled by your provider. You pay that provider for that, right? You don't want to run your internal interconnection in your domain and make sure this works everywhere. There are cases where this happens, but if this does not happen, you can signal this with this field here, which is a priority field, but with the inverse logic than the one we saw before. Low is preferred. So here I am signaling to X that I have both 10.1 and 10.2, but I prefer you to use this exit for 10.1. And here it's the reverse. Here at this exit point, I prefer to use 10.2 here. So let's check if this really works. If we do this announcement and R1 has a packet, the decision process at R1 for the destination 10.2, which route will be preferred by R1? think there is a bug here. R1 has two routes to 10.2, one via R3, learn from R3. No, that's correct. One via R4, learn from R2. That's correct. I'll close in a few seconds. Closing. And the majority says A, which is the correct answer. R1 has two routes to 10.2, this one and that one, and it gives priority, the decision process, unless you tweak it differently, but in all softwares that we have experience with, it tests MED before the test whether Ibgp is better than Ibgp. So it will prefer, so those two routes here, one is learned via Ibgp, the other one by Ibgp, but the MED field will give priority to this route. So this is how we can revert the logic that says we prefer a route learned over Ibgp. Well, we first test whether the outside network is indicating some preference, which means that any packet to 10.1 will be going via this link, and any packet to 10.2 will be going via this link. So which means we are instructing our ISP to do transit for us inside the ISP domain instead of sending or doing hot potato routing. But the multiple routes exist. So for example, if this router crashes here, what will happen? Let's follow the sequence of events. Well, the keep alive mechanism will detect the crash here, or some other mechanisms, perhaps also the lower level beaconing mechanism may detect it. Therefore, R1 will cancel the route, all those announcements that are kept into the RIB-in. R1 has remembered the other announcements, 10.2, which was not preferred, is not the preferred one, but is still in the RIB-in received from R2. Therefore, now since it's the only one, it will be kept. So R2 now has only one route to 10.1 and 10.2. So it will be this one here. And all traffic to this prefix will be sent via R2. So inside the provider domain, we will reach the customer at this link, which is not the intention of the customer, but since the other link does not work, at least at the BGP level, this is what will happen. Now, perhaps there will be destination unreachable inside Y. We don't know. There's no connectivity here. If there is connectivity, then at least we will be able to use this backup link. I just skip those here. A related question: what happens when a BGP router loses its best route to some destination for whatever reason? For example, not because the router is dead, but on this example here, the link goes down, for example, because perhaps the router AS2 is dead, but AS4 is not dead, or in the previous example, the router R1 or R2 in the domain X have lost some routes. What do you expect them to do? I'll close the poll in a few seconds. Closing. And the correct answer is B, of course. So there will be an active withdrawal of the message of the routes that has changed or that has become modified, which means that whenever there are modifications somewhere in the interconnection map that may change routes, and then all BGP routers all of a sudden have a burst of work to do to propagate those new routes, which is in fact one of the limiting factors of the connectivity in the internet. The time it takes to propagate all those routes is limited by the processing needs of the routers here. A is, so the keep alive serves another purpose. It's just saying here, I'm here. We've seen that in OSPF, we did things differently. In OSPF, we periodically send the local database, but of course the local database is expected to be smaller in OSPF unless we do redistribution. This leads to a number of problems. So BGP is a bit like TCP, is one of the central components of the internet. So it has zillions of optimizations and huge complexity. It is less complex than TCP because there are fewer manufacturers who care about BGP, essentially Juniper and Cisco, perhaps also Google and Facebook. But typically Google and Facebook go to Cisco and Juniper for BGP. For TCP, they do their own. One of the issues that I've just mentioned is what happens is the active withdrawal of routes. So it can happen that there is a bug in a BGP router that leads to, when we all know this, when your computer starts or an application starts, then it crashes because it reaches a condition that it doesn't like, and it reboots. If you have something not too smart, it will crash, and that's the end of the story. If you have something smart, it will crash and reboot and try again. I say something smart. Perhaps it's not so smart to try again, but that is exactly what happens in the internet. There can be what is called route flaps. Route flaps are routes that are withdrawn. So one router has a peer that crashes. So we just saw that if that happens, this router will inform all the neighbors, I've lost a route, or I have changed my routes now to some other destination. And that peer that had crashed is rebooting, so it comes up again, and then I have now new information. So you see that we can have frequent changes that will propagate everywhere in the internet, or at least to a large part of the internet. So this is typically called by unstable processes. And that should be avoided, because of course, if that happens, we are essentially polluting the internet. It looks like a denial of service attack. We're sending to all BGP routers, add this route, remove this route, add this route, remove this route. And probably because this is all asynchronous over routers that are sometimes not on the same continents. So there is a delay in all those interactions. So probably even the routes that are being updated do not have enough time to become consistent. We've seen when we talked about OSPF error condition, we see that during the period of time where something has been changed and the routing protocol adjusts to it, there might be routing loops or routing inconsistencies. So this probably happens also here. To avoid this, the solution that is taken is to damp it. That means to wait a bit by detecting and then wait. How is this done? An additional attribute of every route in a BGP router is a penalty. A penalty value is a value associated with a route, so it is 0 if this route doesn't have any problem. But whenever a route is withdrawn, like here, we see the W event. On the x-axis is time, on the y-axis is the penalty associated with a route that is multiple times withdrawn and received again. So the U means we receive an update that reinstalls this route. So we see there is one withdrawal, then the route comes back, it goes away, it comes back, etc. So 4 times in a row we have this event, which is exactly this pattern that I described before. If that happens, whenever the route is withdrawn, we flag it, we increase the penalty by a fixed amount. And then, like anything in human society, all penalty you have tend to fade out exponentially over time. So this is also implemented in BGP. There is, whenever, of course, we don't actively change that every microsecond, but whenever we examine this route again, we will recompute the penalty. So here, the penalty decays exponentially. This is shown here, but there is again a withdrawal. So the penalty increases, then it decays exponentially until there is another withdrawal. And then at the 4th withdrawal, this is the value of the penalty. Here at this time, the route is withdrawn, which means that a route which is withdrawn is in fact not deleted from the rib in. It is kept in the rib in with a penalty value. And then the route is installed again, and then the penalty decays exponentially. And then the rules are, when you hit, when the penalty hits the suppress limit, then the route is suppressed. So a route has another attribute, which is a Boolean, suppress, which is true or false. When suppress is true, that means the route is here, it's present, but we don't consider it because it's an oscillating route. We don't consider it until the suppress flag will become false again, which will happen in this case if the route is stable again after some time. When the suppress limit is hit, the route is suppressed. In order to be reactivated again, we need that the reuse limit is reached from above. And of course, there's a difference between the two that gives a hysteresis system. Otherwise, we would have oscillations. We would not solve the problem. So in this case here, this route will be suppressed at time t1. So this oscillating route, we allow 2 oscillations, then we kill it. And whenever the problem at the remote routers is fixed, then at this time, plus some delay, the route will be reinstalled again. So this is mitigating the problem. Of course, it's not really ideal. We see that during this time here, the route is now up and working normally. It takes all this time to get it back normal. This is how things are. And this is why sometimes there are black holes in the internet. But this is mitigated by the fact that there is a huge connectivity in the internet. So I've mentioned private addresses, and private addresses can exist. So typically, we don't see them a lot, but you can use BGP inside a very big domain to carry even your private address. You can even go beyond, and you can have what is called private AS number. So a private AS number is a special range of AS numbers that are very much like the private addresses. They're not supposed to be used globally. And where can that be used? Well, there are 2 ways you can use it. One way, for example, is when you have a client that is a stub to a provider, like EPFL to switch here. EPFL has only one provider, which is switch. So whenever EPFL reaches the rest of the world, it's always via switch. So EPFL uses BGP to transport its routes, to announce its routes to the switch. But EPFL does not need an AS number. That's an optimization, because any route will be eventually via switch. So for the rest of the world, EPFL appears as if we would be in the AS of switch here. But to run BGP, we still need an AS number. We need an AS number, for example, because we've seen the different rules of BGP, required to know whether something is reached via eBGP or IBGP. The way you know whether the BGP peering is external or internal is by comparing the AS numbers here. So we give an AS number to EPFL that is visible only to switch, and whenever switch announces the route further, it simply deletes this AS number or replaces it by its own number. Both are possible. Another way to do this is also to do what is called a confederation. A confederation is when you use BGP internally into subdomains that you treat as if they would be separate ASs. So assume you have a large domain here. Then you could structure your large domain into virtual domains, virtual ASs that you will treat using the rules of BGP. Why would we like to do this? Well, in order to solve one of the big problems of BGP, which is the size of the IBGP mesh. Remember that BGP requires that all BGP routers in a domain are directly connected by TCP connections to all other routers. If you have a large domains, this is not efficient. There are better ways of propagating information inside the domain. We can have a hierarchy. And here we can build a hierarchy by creating virtual subdomains. Here, for example, I'm showing one big domain that is configured with 3 subdomains that have AS numbers P1, P2, P3. And then you run IBGP between a subdomain and eBGP between subdomains. And you must just be careful to configure that there is 2 types of eBGPs here in this setting. there is the eBGP between subdomains and the eBGP between a BGP router and the true outside. And when we are in the true outside, we must make sure that those private BGP prefixes are removed here, and either removed or replaced by the global AS number that this system has. So this is a very simple way of avoiding the IBGP mesh. It's called a confederation. For some reason, there are two ways of avoiding the IBGP mesh. One is called the confederation. The other one is called route reflectors. That does exactly the same thing, except it's not cheating with terminology. So why it's done in this way, it's not entirely clear to me, but perhaps to avoid misconfiguration, because now you start thinking of eBGP as something being internal to your domain, so perhaps it's not clean. So an alternative to that is to have what is called route reflectors. A route reflector is one specific router in a cluster. So here we call them clusters and not subdomains. So you cluster your BGP routers, and inside the cluster, they do the IBGP mesh only inside the cluster. So or more precisely, inside the cluster, all BGP routers use the route reflector as a central system to which they bring their BGP announcements. So if this eBGP announcement learns from this router, will be passed to this route reflector, and all other routers, BGP routers in this cluster, will receive it from the route reflector. So you will not have a full mesh, but simply you are connected to the route reflector, which of course poses problems. The route reflector becomes a single point of failure. So you need a primary route reflector and a backup route reflector. And you need to know whether the primary is working and the backup is not working. So there is some complexity associated with that. Question? So the question is, what's the difference between this and OSPF with multiple areas? It's the same philosophy. It's been done independently, but it's a bit different because it solves a different problem. In OSPF, we don't require that every OSPF router exchanges its information directly with any other OSPF router in the domain. It will just talk to its neighbors, and the neighbors will also talk to their neighbors. So the complexity for an OSPF router is to manage their neighbors. Whereas for a BGP router, the complexity is to talk to all BGP routers in the domain. The only problem is to detect that it's a problem. Once you detect how it's a problem, how do you do that? If you're creating some software, you have many, many modules that need to exchange information with any other module, then you create perhaps a central mailing system that will gather all the messages and send them to all others. This is exactly what is done here. The complexity is really the reliability. You don't want a route reflector, to be a single point of failure. So you typically have at least two in a cluster. Yes?
To make some changes to the cluster, because kind of violating the assumption that all the routers are connected.
Exactly. So when we do this, we violate the assumption. The IBGP mesh is not directly done. So every router here does not have a TCP connection to every BGP router. It has only a BGP connection to its route reflector. And all route reflectors then there is a full mesh of all the route reflectors. All route reflectors speak to all route reflectors. So in some sense, you delegate to your route reflector the job of doing the IBGP mesh, which means the IBGP mesh in that sense here is a fiction. It's not reality, but I hope you forgive me this. If I explain all the details from the beginning, it becomes completely ununderstandable. I think it's easier to understand that the mental model is there's an IBGP mesh, and to avoid some of the scalability problem that it does, we have this. So this is visible in the software. We'll not do that in the lab because the last lab is shorter. But when a BGP router here, when we examine a BGP router, apart from the fact that it's configured to use a route reflector, all the rest is exactly the same. So it will be all the routes that it has received, for example, from this eBGP router, it will be marked as a route coming from IBGP from this router here with the next stop here. So it's only the messaging system that will be a bit different. There are also other things that are, so we've seen here the route reflectors. There are similar things in what is called route servers. So route servers are things that exist at interconnection points. So the optimization of the internet led to special things that you may have heard, like May West, May East. Those are the critical points of the internet. If terrorists destroy those, then we will have visible and important impact on the internet. Because there are many providers and because there is a need to have many interconnection, it is more efficient economically to have places, companies, in fact, here's one of them, the Swiss IX, that specialize into interconnecting providers. So Swiss IX is a, I don't know exactly where it is. Usually it's fairly secret where they are exactly. But it's probably in the basement of a building where there's a room with a lot of racks and servers here. And if you start your business as an ISP and you need to peer with a number of other ISPs, instead of pulling wires to all ISPs, to Swisscom, to Sunrise, to and perhaps also non-Swiss providers, you can simply connect to this place here. So you go to this place, and at this place, all providers who are present in Switzerland are present. So they interconnect with each other. Of course, you pay a fee to this company, but that's an optimization. Instead of having, it's a bit like the Ibgp mesh, now it's the Ebgp mesh. Instead of having everybody connecting to everybody, pulling wires in all directions, you go to a central location where somebody does it for you. And that leads to a situation like this. Inside peering points, you have a number of providers. Each of them, in theory, comes with their router, and they all interconnect to each other. So inside an interconnection point, you also have an Ebgp mesh. And one solution to avoid this Ebgp mesh is to also do a server that's called a route server that will be exactly like a cluster head in for solving the Ibgp mesh. So instead of having Swisscom connect with Sunrise and with Switch and with AT&T, Swisscom will connect to the route server, and the route server will pass the information to all the others here. So this is what is done. And in fact, it is the route servers that very often give us visibility of what is happening in the internet. Oops. Yes. Let's say a few words about the security of BGP. I mentioned the fragility, perhaps, those interconnection points. There are big ones in the US. Those are precisely May West, May East, where all providers connect. If they are destroyed, then of course we lose a lot of connectivity. But there are also other attacks that are possible. Here is one. Assume you have a malicious ISP. You can say, how could an ISP be malicious? Well, of course, Swisscom will not be intentionally malicious because they would quickly be out of business. But malice can exist either because, for example, a Swisscom employee that was just received a letter that she is fired at the end of the month, and the Swisscom management is not smart enough to remove all the access rights of this employee. So this grudge employee might start doing bad things. So in fact, many attacks on the internet are internal, because there are so many protections to protect the systems, in particular, perhaps not everybody's PC, but to protect the routing infrastructures. So all attacks, not all, but a huge majority of attacks are in fact due to employees who know something and have a reason to misbehave. So it's not quite impossible. There are also, because I mentioned that some providers are under the control of governments, and all this interconnection with beautiful mental model where we're all computer scientists and we love each other and we obey by the rules, and the only bad things that happen is crappy people who don't really understood well and did it. That exists, of course, but there are also conflicts between states, and that may lead to that kind of thing. So this is based on a historical example. There's a paper that describes this, where one country did not like some YouTube videos that they wanted to forbid to their the citizens of their country. So they did an attack on the YouTube servers by sending here, injecting here false paths here. So this malicious AS injects, for example, those two announcements to EPFL, and assume ISP1 accepts them. So what do you think will happen for traffic from C1 to EPFL? So customer 1 is a customer served by ISP1. ISP1 has been the subject of this attack here. What will happen? Will this attack work? Will it work partly? Will it work? Will it be defeated by the beauty of BGP? Of course, if you're trying to prevent access, if you hear ISP3, if it receives traffic, will of course not forward it to YouTube, but will simply send a banner saying this is forbidden, or simply drop the traffic. I close the poll in a few seconds. Closing. Now there's a tie between A and B. Well, the truth is we don't know because of aggregation. Right? Here, EPFL probably, which is here somewhere, is probably advertised in the internet as 128.178/15. Right? So here this guy is advertising two more specific prefixes. And since they are not competing with the EPFL ones, because EPFL or switch for EPFL has advertised another one, we've seen that a sub-prefix of a prefix is considered as a different prefix. So they're probably accepted, except if there are security mechanisms that we will discuss. If we don't have this security mechanism, and in the example, the historical example that I alluded to, they were accepted, so ISP1 will accept both. Now what will happen? A packet from C1 that goes to EPFL, we will do longest prefix match. We will have the correct announcement that leads to probably ISP2, and then the wrong announcement that will probably lead to ISP3, because by longest prefix match, we will go here. In particular, this will be true if ISP1 does not do aggregation at the BGP level. So if ISP1 accepts those two prefixes and sees, oh, there are two prefixes, but they are overlapping, I could aggregate them. If we aggregate them, then we would have competing prefixes, and then perhaps then the rules of BGP will decide. It's hard to know exactly what will happen, but probably the shortest path will lead to this one here. But if they are not aggregated, they are distinct prefixes. So it's an example of an attack. You do, instead of attacking the entire prefix that you want, of a domain that you want to attack, you attack a very small part of it. And because it's more specific, you will not compete with the others. If it's accepted, you will attract all the traffic that goes this way, which is what had happened in this example. It was a country that attacked YouTube and did more specific prefixes and was able to attract all traffic to YouTube in order to, of course, not serve it. Well, we will see how this can be defeated with the security mechanisms of BGP after the break. So we'll do a break and resume at 1:15. We have seen an example of attacks against BGP. And those attacks can be used to deny service, but also to spy or forge messages. So other countries did that for forging some messages. Of course, there are techniques to avoid this. So the first one is the fact that addresses are not randomly allocated. I mean, when this ISP was advertising EPFL, that should have seemed strange because this ISP is not owning this block of addresses. IP addresses are allocated to regional registries. For example, in Europe, it is RIPE, which receives, for example, the EPFL addresses that we have, the EPFL, the address you may have at home from your provider. They are part of blocks that were allocated to Europe. So RIPE maintains a routing registry of who owns which block of addresses. And this Internet Routing Registry, the collection of all those information, can be read by all providers. So if you're a provider that receives a BGP announcement of a block that somebody says, I have this block of address and the path is just me, that means I own this block of addresses, then it's easy to check whether it's true or not. So this is the first countermeasure. It's not cryptographic, and it's best effort in the sense you're not certain whether everyone will do it. But the providers that do it might avoid some of the attacks here. Of course, this is very minimal. You can go one step above by having a true authentication of the blocks of addresses. For example, very much like we've seen for certificates. If I go to a website, I know this website was given to my bank. For example, this DNS name was given to my bank. This is what we saw when we discussed how TLS works. Here, there is the same thing for blocks of addresses. For example, Switch receives this block from RIPE, that's for IPv6. Then it obtains a certificate from RIPE and can use it to create and publish what is called a route origin authorization, which is a message or a block of information that guarantees that this block belongs to Switch, and this message is signed by the public key of RIPE, which is itself well known by all registries. So any AS can verify this certificate. We can see this here. For example, if we go to a place where we can see an announcement that has been received by some, here it's Hurricane Electric, that has received an announcement for Switch. Then if you go to the websites that I will mention here, you can see whether they are verified or not. So here this key means it was signed and valid. So the origin AS, which is here the AS number of Switch, is guaranteed, as long as cryptography is not broken, is guaranteed to be truly the owner of this block of address here, which will mitigate at least part of the attack. So this is in deployment. So many ASs are actively using these cryptographic signatures to have a certification of route origins. But this is not sufficient because we might receive an announcement from somebody that's on the path. So you could forge path, not just the origination of a route. So this is another story. This, in principle, we should authenticate not just the origination, but the entire AS path. If Switch forwards this message to another provider, and this provider provides it to yet another provider, we should sign all the modifications, all the additions of this AS paths that are done here. Otherwise, it will be easy for somebody in between to forge a wrong AS path here. That's another story. The reason for that to be much slower, so this is in progress, but it happens very slowly. The reason is that now you need to verify all the fields that are received in BGP announcement. If a BGP announcement has 6 different ASs, you will need to verify the complete thing. And the BGP routers have CPU performance bottlenecks. So this is in progress, but has a considerable cost on the cost impact on the BGP routers. So security is really the weak point of BGP. Because of that, there is an alternative to BGP. I mentioned that BGP is the only format that exists today. There is an alternative that is deployed largely. Most of it was developed in Switzerland at ETH by Professor Adrian Perick in the project called Cyan. Cyan is not just an alternative to BGP, it's also an alternative to IP. It redefines the IP layer, so it's IP version 7 if you want. Because of that, there are big questions whether Cyan will be successful or not, because we see going from IPv4 to IPv6 is already not so easy at all. So getting to yet another version is not certain. I hope it will succeed, but we will see that in 20 years. I will not be here and you will not be here, but perhaps you will be involved with that. Here it's an alternative to BGP, where anything that is done, any message that is done, is signed. So we redesigned from scratch instead of having this strange model of BGP injecting the routes at the same level and everything. We use source routing heavily. So we will route to a border router somewhere, and we can verify all the steps that are done in between. SIGN is completely different from the IP architecture, although it reused some elements. So in this course, we don't have time to discuss in detail, but if you're interested, I encourage you to go to this here. It's not so easy to read, but it's certainly very interesting. And the future will tell whether this or other similar attempts to radically solve these security problems of BGP will be possible. Right now, the BGP problems, as I said, are solved by the mechanisms of origination validation by cryptographic means, but also other means, or where some providers may use what is called deep monitoring techniques with machine learning techniques in particular to address whether the things that we see are plausible or not. It's not as strong as having complete authentication of everything, but these are an orthogonal dimension of security that you need anyhow. You cannot simply rely on cryptography to secure your network. There is a vision of BGP, of the AS interconnection in Switzerland, at least seen by Switch. So you see that Switch has different interconnections to the rest of the world, and here are the other networks to which Switch connects. So you see that there are several interconnection points: Basel, Zurich, Geneva, and Lugano. And also here, I guess. Not sure what city is here. Rorschach, perhaps. You can go also to some providers like Hurricane Electric that gives that publish the BGP information that they receive. So of course, the BGP information that you see is only based on where you're watching it. So the world is not the same depending on where you observe it, but some route servers in particular are publicly available. So you can go there and see, for example, all the routes that it sees and check, for example, whether Switch has something or not. You can also see the number of prefixes that are seen by this provider. This was 2 months ago. You see that the number of IPv6 prefix is a bit below 200,000, and the number of IPv4 prefixes is getting close to 1 million. So 1 million IPv4 prefixes and 200,000 IPv6 prefixes. This is the size of the BGP routing information base. This is why redistributing that in OSPF is sometimes not done. So BGP is heavy. We will see that in the lab. In the lab, it will be light, but you will not have millions of prefixes. But that is the major problem. Why do we have much more prefixes in IPv4 than in IPv6? Well, a bad answer would yes. A good answer. IPv6 is not deployed everywhere, so it's too young. So in some sense, that's why it's not. Well, I'm sorry, but this is really the bad answer. Although it's true. But yes, because of aggregation. So IPv6 is designed with aggregation in mind. So, for example, Switch in the world announces 1 prefix in IPv6 and announces 20 prefixes in IPv4 that are discontinuous, so cannot be aggregated. So that's the reason. So aggregation is really a hot topic in BGP, and all the route servers, they publish metrics of how good ISPs are at aggregating. Because if you don't aggregate, of course, your job is easier. But then the size of the tables for the rest of the world become larger. So you make your job easier, but more difficult for others. We know that in other settings. So aggregation is a real problem. And here we hope. The hope was when IPv6 was standardized in 1997. It was drafted even before. In 1996, I was already doing labs on IPv6, but we see it's very slow to become pervasive. The hope was we would get there and we disconnect this one. So this will happen one day. The IPv4 will get disconnected, and then we are back in here, and we can have more lightweight BGP routers. But in order to get there, we will need these very powerful BGP routers. So that doesn't really solve the problem. Voila, that's the end, at least of the theory part on BGP. BGP is really the central component of the internet. This is where all the different connectivities take place. We've seen also that the interface between BGP and interior routing protocol is complex and has many subtleties, and that the security of BGP, well, is not yet fully complete. We will talk more a bit later about the interactions between BGP and Mpls that we very briefly discussed today, and virtual private networks. We will see also funny things where BGP is used for managing this. And I mentioned also that beyond BGP, perhaps someday there will be SIAN that will replace BGP, perhaps or perhaps not. I hope it will, but displacing existing things is very difficult. As I mentioned, SIAN uses source routing and systematic encryption. Source routing solves many of those problems of the complexity of interacting between BGP and IBGP, and systematic encryption solves the security problems. Voila, that's all for this part. The next topic is radically different and is the application layer. The application is more funny, of course, because that's what we do with the internet. BGP is just under the hood. I call it application layer, but in reality, I'm cheating a bit because we will also discuss QUIC, which is for me really transport layer, but officially in the layering scheme is not transport layer. We'll talk about it. So the application layer is anything useful that we do with the internet. In Lab 3, you did programs, so you coded your own application layers. The web, of course, is the most well-known application layer. And for users, the web is simply HTTP. And HTTP evolved from HTTP 1.0, 1.1, and HTTP 2. And HTTP 2 allows to use the same TCP connection for several objects with parallel processing of requests at the application layer, which means this is why HTTP 2 is very complex. We'll not see in detail. It's not the focus of this course. But with HTTP 2, we're able to multiplex several streams of interaction, whereas with HTTP 1.1, we essentially had a simple question and answer protocol. Much of the complexity of HTTP 2 is put into QUIC, so we will discuss it into QUIC, which does this similar thing. But before getting there, let's see why there is some complexity by asking the following question. Assume we connect to a server, and the server sends a web page that has 10 embedded objects. Modern servers are invariably like this. If you have WordPress or whatever, you don't send a web page. In fact, you send a script with many links, objects. Perhaps some servers even have the bad taste of adding a sound to the place where you connect. So, but the embedded objects are very often scripts or pieces of scripts. And HTTP typically uses a single TCP connection. Now, assume the browser displays the element of the page as soon as they arrive, and one packet of the first object is lost. Of course, because of TCP, by virtue of TCP, it will be retransmitted. But what will happen next? close the poll in a few seconds. Closing. The majority says A, which is perhaps the understanding of the people who developed HTTP2, because you can multiplex multiple objects. But if you use a single TCP connection, what will happen is B. Right? Because remember, TCP offers a streaming service. You're saying if a packet is lost, all the things behind are invisible to the socket. So even if you have HTTP2 that allows to do multiple transactions in parallel, all the rest is as if it had not arrived. So it is possible in parallel, but all the other threads are waiting for missing data. So this is, the correct answer is B. The second object must wait for the first object to be completely received, not so much because it's second versus first, but because in the order that they were originally sent, this is what happens. That's a problem of, that's a problem of TCP, and that's one of the multiple motivations to develop QUIC. So QUIC is a replacement to TCP that in particular will avoid this problem that we said before. But QUIC has another also motivation. It is to integrate security, right? Remember that when we navigate the web, in principle, we use HTTPS, except if we're very bold and we have an extremely secure machine that cannot be attacked. We use HTTP over TLS, and TLS is over TCP. So we first open sockets, the sockets are wrapped, we open the TLS thing, and then we can do the HTTP, which will give at least 2 RTT, very often much more, before being able to send any piece of information. QUIC will avoid the problem, or will try to avoid the problem by doing things the other way around. So QUIC will open the QUIC connection, which is a replacement for TCP connection, at the same time as it does the security handshake, which makes a lot of sense. I mean, it's much more complicated. Once you agree, you have on authentication parameters and you've checked that the other end is what they do, you have done much more than the handshake that TCP is doing. So you can subsume the TCP handshake by putting all the information in the exchange that you do for security. You're doing much more complicated things. The very trivial things of TCP to agree on the MSS size and the initial sequence number, they could be put into the initial security handshake. This is exactly what QUIC does, which means QUIC does not use TCP. QUIC uses UDP. If QUIC had been invented 30 years ago, QUIC would have been called TCP version 2 or something like this. So it is really a transport layer. But for reasons that are due to what is called middle boxes, like filtering routers, we use UDP, because now there are lots of boxes, like your ADSL modem at home, lots of routers. If they see a field that seems weird in a packet, they kill it. So if you invent a new version of a transport layer by giving a new transport number, you need to make sure that all boxes in the world will be updated, which will be okay for the Facebook and Google boxes. They can update them on the fly. They have automated tools for doing this. But my ADSL modem at home probably would not work, right? Because by the time Swisscom has done a new release and updated it, and I would have a service interruption, etc. So it's a bit tricky. We find again the problem that I mentioned about Cyan displacing BGP. Cyan is certainly superior to BGP. Will it displace BGP? Well, you have this problem. How do you displace something existing? Here's the same reason. So this is why QUIC was developed by Google. And so the Google people are smart, as you know. So they decided to do over TCP. So QUIC will open one. In fact, it uses exactly TLS, except TLS is done on TCP. So it's a modification of TLS that does not require TCP to work. But at the cryptographic level, it's exactly TLS 1.3. And then it will first open the connection and then work. One side effect is that it doesn't work without security. So you cannot open a QUIC connection without security, like we can do with TCP. I can have a server and a client, open the connection, and transfer data, like we will do, for example, like you're doing in Lab 5. With Quick, this is impossible. You must first secure everything, which is by design. The side effect is also that you have only one handshake. So if you run HTTP over TCP, so HTTP version 3 is the version of HTTP that is made to run over Quick, then it's much faster. The first get you do comes immediately after one handshake instead of, in the best case, 2. And you can try it if you're using a Google app. You probably are using Quick. But Quick does another thing. It solves the problem that we saw in the quiz. It allows to have multiple streams. So it doesn't, the TCP problem is that it's stream oriented. So we could say one way to solve that is to make it message oriented, like UDP is. Quick did not go that way. Instead, it says I allow multiple streams. So a stream is like a single TCP connection, but under the same Quick connection. So if you have the example I mentioned before of a web page that has many embedded objects, then what you can do, what HTTP 3 will do, is for each of the objects that it transfers, it will open a new stream. So if you have 10 objects to transfer, you will have 10 streams. If one packet is lost in the first stream, it will not affect stream 2. So you will not have this stupid blocking because the banner or the sound is blocked somewhere, the whole page is freezing because we don't have the JavaScript to open the box somewhere because something is lost in another packet. So that makes also HTTP 3 much simpler than HTTP 2. We don't need to multiplex things because the multiplexing is done by Quick here. So that's the major second difference. Other than that, it's like TCP with difference in the detail, but other than that is TCP. Still, the one Quick packet can contain data of multiple streams, very often not, because a Quick packet has a given size, 1280 bytes minimums, up to 1500 if the end-to-end, if the path MTU allows. So very often it's not possible, but if you have small data, for example, very short JavaScript, you may have multiple of them in the same packet. Here. Of course, if this packet is lost, then all the stream data are lost. But if, for example, this packet is lost and stream 5 had a big, it was in another packet, then stream 5 will not be affected by this loss here. Stream 0 is always for the cryptographic handshake. So that's the stream that is used by TLS. So for TLS, it is the same as if it would be running on TCP, except it's running on stream 0 of Quick. And there are a small subtleties, things because it's done now instead of 40 years ago, then we can remove some of the things that we think were after the fact not so good idea. For example, the sequence number is inside the streams, but in TCP, the sequence number is used for two things at a time. It's used for giving in-ordered delivery of data. So in order to deliver the data in a given order, you need to know which piece of data is where. So that's what the sequence number is for. But it's also used as an identification of which packet is lost and needs to be retransmitted. Here, every Quick packet has a unique packet number that has nothing to do with the stream offsets that are given here. And it never wraps because it's very large, 64 bits. And if you retransmit a packet, it's a different number. Remember, in your TCP, there are always ambiguities. When you compute the RTT, for example, you acknowledge data, but perhaps it is the second retransmission of this data. So, and you don't really know when you're the receiver. So in TCP, there are many heuristics that are driven by the fact that we don't really know what happens. Here we break the problem by knowing everything what happens. So when you send a packet, you give a packet number. For measuring RTT, you wait for the acknowledgement of this number. If the acknowledgement comes, you know it's exactly this packet that, and you know this is exactly the measure of the RTT. Of course, a packet can be lost. If a packet is retransmit, it's retransmit with a different number. So there will not be collision in the measurement of RTT, for example. The terminology is that inside, so we use the word Quick connection, a Quick packet, And inside the packet, there are frames, which correspond to stream data. And opening a stream in Quick is nothing. Simply putting a new stream number in a frame is opening a stream. So you don't have a handshake if you open a new stream, for example, because in a way, an HTTP page has a lot of multiple objects. Then whenever you see a new object and you create a new stream to send it over, to send it, and there's zero overhead for creating a stream. Flow control is per stream and per connection. So remember that flow control is what is done with the window field of TCP. This is the thing that prevents a server from being a receiver from being overloaded by the amount of data that is sent by the source here. So you do that per stream and per connection using a mechanism that's very similar per connection that has to do with the equivalent of a socket. Unfortunately, Quick doesn't use socket. That's why also we don't do a lab with Quick. Using Quick is a bit complicated. It's a library. You need to use a function library, which is well done in C++. In Python is a bit more complicated to use. So per stream Quick socket, if I can say, you have a given buffer size that will be reflected by the explicit offset that you give, and also per stream. Congestion control, in contrast, is per connection, which makes sense. If I'm transferring 10 objects in parallel, what matters for congestion control is the fairness and stability of the internet. So here we treat a flow as a connection. And apart from that is the same, exactly the same as TCP. So all possible variants exist. The original Quick was doing TCP Reno because the people who designed Quick, they say, let's be safe. We're doing something radically new. So let's use the oldest version of TCP New Reno, which is the oldest version of TCP that worked reasonably well. But very quickly, there was a version of Quick with Cubic, and now there are versions of Quick with BBR also. BBR is a bit shaky, but since it's done by Google, obviously, there must be pressure to put it also into Quick. If you read the literature, the Quick designer said there will also be unreliable streams, but so far they don't exist. Unreliable streams means if you use it, for example, to do a DNS request, you send a message to a DNS server, you would like a reply, you don't want to have reliability at the transport layer because the DNS resolver expects an answer. If the answer doesn't come, you will detect that, well, you don't know why it doesn't come, but you will ask again. So there is no point asking the transport layer to ask again, given that the root of the message will ask again. So in fact, it's counterproductive in a case like this, because you might be sending again at the transport layer a message that is completely useless because the application layer is resending it. So because of that, it is also foreseen to have unreliable streams. And there was an example of a master thesis done at TPFL on exactly this. In the context of industrial networks, you have sensors that send information every, for example, 20 milliseconds in the example that was here. If this message is lost, well, it's bad, but it's not a catastrophe because cyber physical systems typically are able to be robust. But there is no need to retransmit it if a new message comes. If the round-trip time is 3 milliseconds and a message is lost, it's a good idea to retransmit. It's better to receive the retransmitted message with 10 millisecond delay than nothing. At least in some cases, it may be better. You don't know how the other end is working, so it's a good idea to do this. But if your sensor has produced a new measurement and the logic of your applications is you always use the newest measurement, there is no point having the transport layer retransmit an old message. That one is useless, and second might congest the channel and will delay the arrival of the newer information. That's exactly the problem, and this is why you would like to have unreliable, what I mentioned, unreliable channels when if you use Quick, for example, to access the DNS. Here, this solution called ephemeral Quick consists in simply saying we send one measurement in one reliable stream, which means if it's lost, it will be retransmitted. but we do one stream per measurement. We can do that because now streams have zero overhead in Quick. So we can open as many streams as we want. It doesn't cost anything. And if a new measurement is available, you kill the stream by sending a reset and the previous stream. And if the previous stream has not been acknowledged, then you simply kill it. So that would be an easy way with Quick. That's the kind of things that Quick can enable here. But does it really work in everyday life? For example, if you're sitting like Lisa behind a NAT and you use YouTube, is it guaranteed that it will always work? Or do you need to have a Google compatible ADSL modem or NAT? I close the poll in a few seconds. Concentration on answer C, which is the correct answer. Of course, Google was smart enough to make sure it works with all NATs, not just some NATs. Sometimes in the lab, depending on your configuration, there are some difficulties that are due to the NATs. In the labs, we use NATs to interconnect to the guest operating system, and you may use a NAT also if you're at home, and sometimes there are combinations that don't work, or sometimes ICMP messages are lost across a NAT, etc. But fortunately for Quick, this is not the problem, and this is because UDP is below Quick, so the UDP port numbers are visible. Everything above UDP is encrypted and is not visible by the NAT. That cannot do anything about it. So a Wireshark of a Quick session will simply show a UDP flow exchange. Right? You will not know that it's Quick, although you might guess it because this is the TLS port with UDP, which is probably Quick, but there is not a specific port number for Quick, just like there is not a specific port number for TCP. So, of course, this will work. And by the way, we see here that my conjecture is that in the future, TCP will supersede TCP. At what speed, I don't know. I'm having observed how hard it is for IPv6 to replace IPv4. It's also hard to say how fast Quick will replace TCP. But certainly, there is no benefit of TCP compared to Quick today, other than the interface and the stability of the software. The socket interface is very, very well defined. But in terms of performance and service that is offered by Quick, it offers everything that TCP does and more. Yes? So the question is, are there easy to use libraries of Quick? In my knowledge, no. Not as easy as what we do in Lab 3 with the sockets that are really very simple. It's a bit more complicated, but it's also not too complicated. The problem is there are many different environments, and they are not all addressing the same version of Quick. So, because Quick is still in development, unlike TCP, where the sockets have been around for 40 years. But it's, don't misunderstand me, it's not monstrous of complexity. It's quite doable. Yes, question? Yes, exactly. Quick, in fact, because Quick now has this Quick packet number, it is able to also to identify all the missing gaps in all the streams. It has up to 256 SAC blocks, whereas TCP has only 3. So you can exactly say, I'm missing bytes this to that of stream 3 and bytes that to that of stream 4 and retransmit them exactly. So some of the TCP heuristics are not needed, like fast retransmit with 3 duplicates, etc. This you don't need. You know exactly, as soon as you receive a NAC, you know exactly what is present and what is not present. But you still need to know when nothing is coming, whether you should retransmit, it's a delay or a loss. So you have similar heuristics, also tail loss, tail drop detection, etc., whether it's the last package of an exchange that is lost, etc. So Quick is practically reusing everything from TCP, but it does it per stream. So I invite you to test Quick in the different references I give in the slides. Of course, you need today, as far as I know, although Apple says they are working on it too, but today, as far as I know, it's essentially Google software that uses Quick, which is a large fraction of the software. For the YouTube app, you can do a Wireshark and you should see a Quick packet. Of course, Google is, as you can imagine, fancy, so they will try every possible version. So your YouTube app will first try Quick by trying the TLS handshake over UDP. If it doesn't work, that means Quick doesn't work for some reason that we can discuss. Then it will try TCP and do it the correct way. Why would Quick not work? Quick will work because over modems and NATs and so on. But there are cellular networks that do lots of optimizations due to TCP. We'll discuss some of them in a minute when we talk about the application layer transport gateways and transport gateways. But you remember that TCP has performance problems, by the way, that Quick has exactly the same. Quick solves only the security double handshake and multiple streams. I mean, all the other problems of TCP are exactly present in Quick. So it's not the end of the story. But one of the problems of TCP is the bias against long round trip time, and also the fact that TCP reacts to losses as if there would be congestion. So this is solved by some cellular operators by offering a TCP proxy service in their network, where we cheat with TCP when you send a packet the acknowledgement, for example, will be sent directly by this TCP proxy instead of coming from the other end. So that will keep your window increasing, even if a packet is lost. We will see also an example here of application layer gateway. So this is done by some operators, not all, but some. Orange, for example, does it a lot. Now this breaks Quick. Of course, Quick cannot be broken in the middle, because in Quick, everything is encrypted. If you use TLS over TCP, you can manipulate the TCP by faking an acknowledgement, even sending an acknowledgement that is not being received because you hope it will come soon. So all those things you cannot do with Quick. So Quick is not compatible with this cellular network optimizations, which is one of the complaints of the cellular network operators. But Google says, but you should not look into our packets. Right? It's also not fair. And then the cellular operators say, yeah, but we improve performance because TCP is broken. So it's a non-solved story. Now we will discuss next week the implications of that when we discuss application layer gateway. Right now, let's conclude with another application, which is the DNS. Again, it's in the application layer because formally from the model of TCP/IP, we do an application layer protocol, which is the DNS Resolver. Of course, it belongs to the IP infrastructure in some sense, because we've seen that the goal is to map DNS names to IP addresses. DNS names at the beginning could be only names that came from a very small set of three-letter reserved names or 2 letters for all possible countries in the world. But that was in the past years open. So today, anything can be a DNS name if you buy it. So you can buy your own domain, company, for example, instead of .com. And then you will resell to the people who prefer your name than the .com. And it's a business decision. Of course, your name, you will buy it, will be very expensive. You plan to pay $500,000 per year to have your own name. But if you have millions of customers to whom you resell subdomains, that may be a business. So some companies do it. So we have SUCS, for example. That was a name that was taken by people who wanted to attack companies by creating the apple.sucks, and then they blackmails Apple by saying, if you didn't give us money, so this one was removed. But this is how things are. So it now has become purely business-oriented. How does DNS work? We have seen you know that when we connect to a machine, when we send an IP packet, we need the IP address. So we need to go to a DNS server And we have seen so far the single DNS server, but in reality, we have many, many DNS servers. For example, when IBM decides to have names, it's the job of IBM, same at EPFL. EPFL creates a service called, I don't know, lca2.epfl.ch. The domain epfl.ch belongs to EPFL. The lca2.epfl.ch is associated with one IP address, and that's the decision of EPFL. So we have DNS servers, same for IBM. We have DNS servers that map the names that they have allocated, that this organization has allocated to things, essentially IP addresses. As we'll see that in DNS, there are many, many other things than IP addresses, but that's the essential part that is needed. Now, what happens when somebody at EPFL clicks on an IBM name, like this one here? Then your machine is probably configured with an EPFL DNS server. When you know that the IP configuration, you must give a DNS server. You can use a DNS server. It's typical. Normally, you use the DNS server that is given to you by your provider. If you're at home, the DNS server will be a DNS server that's located inside your ADSL modem or your router that will do nothing else and simply send a query to your provider, Swisscom, for example. That's the normal way of doing it. Some companies like Google, they agree also that you use their DNS server, 8.8.8, for example. Those are, but many companies don't agree. I mean, Swisscom is not happy having the whole world using their DNS server because it's a cost for Swisscom to run this DNS infrastructure. It's also a cost for Google, but Google is so large and they have so many computers, it's just a drop of water in an ocean of server costs. And it gives Google a lot of information on who is doing what, which is the business model of Google. So that's another story. So you have your DNS server, that's part of your IP configuration, and your DNS resolver. Whenever a program starts something, you will do, like we've done that when the socket program, you will have get host by name. So this get host by name function triggers a message to be sent to your DNS server, which is shown here. For example, here, what is the IP address of this? So A means IP address, IPv4 address. Then this DNS server may have the question, but if IBM is not so popular at EPFL, perhaps this information is not available. It's not available because it's not the job of EPFL to have all the DNS names and addresses of IBM. It's the job of IBM. So what the DNS server will do here is ask the IBM DNS server. But there is a problem. How does this DNS server know what is the IP address of the IBM DNS server? There is no well-known address. It would be too strict, too rigid, and it's not in the spirit of the internet. So instead, the DNS server will go up the hierarchy. You see that's www.zurich.ibm.com. I don't have any entry for ibm.com, but I have entries for .com. .com, those are, and all the dot something are the root DNS servers. So in the world, there are a number around 13 duplicates. So in reality, a larger number of root name servers. And those root name server will have the IP addresses of the DNS servers of the domain below. That's the principle of DNS. If you create a subdomain, then you have to know the subdomain will have to have their own DNS servers, and who creates the subdomain must know the IP addresses of the DNS servers of the subdomain. So all the root DNS servers of the world know all the IP addresses of all the IBM and others, and the Switch and so on, and EPFL, and .ch. So my DNS server here will send the same query to a root DNS server, and the root DNS server will give a reply, which will not be the final address, but will be NS record. NS is for the name servers. It will give me the names, which are useless, and the IP address, which are useful, of three DNS servers of IBM. Now, my DNS server works for me in a recursive mode. Recursive means I do only one call to the server, and the server replies only once, but does a lot of job under the hood. If it would be iterative, the DNS server will simply reply to me with that, which would be useless for me, except if I have a DNS server inside my machine. Now the DNS server still doesn't know the answer, but it knows 3 addresses of IBM DNS servers. So it will send one of them, the first one. It will get the reply, and the reply will contain the IP address of the machine I want, and the reply will be sent to Lisa, who can now navigate the web and go there. And of course, the DNS server, as you can guess, will do one thing. It will cache this reply. It will remember. So chances are, in fact, that whenever you do this, you don't trigger all this chain of operations. You will only get this cached value. And this cached value is kept for a duration that is called the TTL, here in seconds. Here it's 2 days, it's 2 hours, 7,200 seconds, that's 2 hours, which was the value when I tried IBM, which is a few years ago, which was the value now. If you are Facebook, for example, you will have a DNS, a time to live value, which is order of minutes, which means that all the cached values in the world will expire after a few minutes. In particular, if your DNS servers die, which happened to Facebook a few weeks ago, after a few minutes, all the cached values also expire. We will see why you want to do this next week. Voila, thank you for your patience, for the small overtime, and see you next week.